Welcome to The Explainer. Today, we're stepping onto the floor of the ultimate high-stakes gambling hall, nature itself. Think of biological traits as nature's way of placing bets. Every organism out there has a limited stack of chips, right? Limited energy, limited time, and limited resources. And how they choose to place those chips pretty much determines whether their genetic line hits the jackpot or, well, goes completely bust.
So it really all boils down to one fundamental question. How does nature choose between survival and reproduction? It's the ultimate game of trade-offs. You know you can't put all your chips on living forever and having a million babies. It just doesn't work that way. Every single species has to gamble its limited resources differently. Some play it fast and loose, while others are incredibly conservative with their bets.
Okay, let's dive right into this. Here's our roadmap for today. First up, we'll look at generalists versus specialists. Then, we'll map out the 3 survivorship curves. Third, we'll compare R-selected and K-selected strategies. And finally, we'll tie it all together by looking at how we manage our natural resources.
All right, starting off with Section 1, generalists versus specialists. Let's look at the daily survival bets these animals are making.
Think about a classic generalist species, like the white-tailed deer. These guys are incredibly adaptable. They feed on dozens of different plant species. And honestly, they don't really care if it's a freezing winter or a sweltering summer. They just adapt their diet to whatever happens to be around. They have a massive, broad ecological niche. But then, compare that to a specialist, like the giant panda. The panda has basically gone all in on one very specific bet: bamboo. It absolutely requires bamboo. It eats almost exclusively bamboo. And if that bamboo blooms and dies off, the panda can't just pivot to eating pine cones, right? Specialization is a brilliant strategy if your environment is totally stable, but the second things change, that narrow niche makes them incredibly vulnerable. And because of that, in our modern human-driven era, generalists are the clear winners. Raccoons, crows, rats, they look at a suburban garbage dump and literally see a 5-star all-you-can-eat buffet. They actually thrive on human disruption. But then look at the vulnerable specialists. The koala absolutely needs specific eucalyptus leaves. The black-footed ferret requires prairie dog colonies to survive. The California condor needs wide-open terrain to soar. When those highly specific bets fail, usually due to human disruption, these are the species that end up on the endangered list.
Moving on to Section 2, let's see how these bets play out over an entire lifetime with the 3 survivorship curves. To really understand this, demographers use a vital tool called the survivorship curve. Basically, it's a graph that plots the fraction of a group, a cohort, that survives to each age. Now, by convention, the vertical axis is plotted on a logarithmic scale. I know that sounds a bit dense, but it really just means that a straight line on the graph represents a constant rate of mortality. It's an ingenious way to clearly visualize the survival strategies of completely different species, all on the exact same chart.
Now, what's really fascinating about this is the profound meaning behind the actual shape of these graphs. As the quote notes, the shape of a species' survivorship curve encodes its fundamental life history strategy. Just by looking at the bend of that line, you can instantly tell when most individuals in a species die, how much parental care they're receiving, and exactly where they're investing their energy. A simple curve tells us if they're playing the long game for survival or making a frantic, massive investment in immediate reproduction.
Let's walk through the 3 idealized shapes you're going to see out in nature. First up, type 1. This is the late loss curve. Mortality is super low early on and really only spikes when the animals reach old age. Humans in high-income countries, elephants, great apes, this is where they sit. They invest heavily in just a few offspring. Next, right in the middle, we have type 2. This is a linear, constant survivorship curve. Songbirds are a perfect example of this. A 1-year-old songbird and a 5-year-old songbird face the exact same daily odds of getting eaten or catching a disease. It's a constant risk. And finally, type 3, the early loss curve. Think of the Atlantic cod as the poster child for this one. A female releases literally millions of eggs. It is a massive gamble, and almost all of those eggs die or get eaten in the first few weeks of life. But the wild thing is, those very few that actually do survive to adulthood, they face relatively low mortality after that point.
So the crucial point here is that adults are the reproductive capital of a species. This is incredibly important for both our type 1 species, like the elephant, and our type 3 species, like the cod. Think about it. For an elephant, taking out an adult is devastating because they reproduce so slowly. But for a cod, taking out the adult is equally disastrous because you absolutely need that adult to release those millions of eggs just to guarantee a tiny handful of survivors.
Both of these strategies are hypersensitive to added adult mortality from things like poaching or commercial fishing. Which brings us to Section 3, R-selected versus K-selected species. Let's dig a bit deeper into these reproductive strategies. First up, R-selected species. That R stands for the intrinsic rate of natural increase. Honestly, the easiest way to think of these species is as nature's equivalent of day traders. They make quick, high-volume bets. They invest heavily in producing tons of offspring, but then they give them practically zero parental care. They're just banking on rapid colonization in unstable, disturbed environments. If the conditions are right, their populations will absolutely explode, even if any single offspring has a minuscule chance of surviving. On the flip side of that coin, we have our K-selected species. Here, the K stands for carrying capacity. So if R-selected species are the day traders, K-selected species are your long-term blue-chip investors. They produce very few offspring, but they invest massive amounts of time and energy into every single one. They're pushing the survival probability of their young as close to the environment's carrying capacity as they possibly can. The catch? Because their reproductive rate is so slow, they are incredibly vulnerable to habitat loss, and agonizingly slow to recover if their population takes a hit. And this brilliantly illustrates why understanding this continuum is a literal matter of life and death for conservation efforts. Because R-selected species replenish their numbers so incredibly fast, they naturally have a pretty high tolerance for harvesting. K-selected species, however, have practically zero tolerance for elevated adult mortality. If they're going to survive, they absolutely require large intact habitats and long protected seasons. Now, of course, nature rarely deals in pure absolutes, right? No species is a 100% pure R or K strategist. It's a continuum. A mouse is highly R-selected. An elephant is highly K-selected. But right there in the middle, you'll find something like the white-tailed deer. It's definitely more K-selected than a mouse, but far less so than an elephant. They occupy this intermediate position, basically adjusting their evolutionary bets based on the specific environmental pressures they happen to be facing. All right, Section 4, managing our natural resources. Let's apply all this to the real world. Let's put you in the hot seat. Imagine you are a fisheries manager. You have to figure out exactly how many adult fish can we sustainably remove from the water each year. Well, the answer depends entirely on the fish's life history strategy. If you're dealing with a large grouper, which is a K-selected species that grows slowly and relies on high adult survival, removing even a tiny fraction of those adults can exceed their replacement rate and completely collapse the stock. But if you're managing herring, that's an R-selected species. They grow fast, they release millions of eggs. That population can sustain a much, much higher harvest rate, just as long as enough adults survive to spawn. Let's move on and see how this builds when we factor in environmental impacts. Because pollution and habitat loss do not hit all species the same way. When pesticides like DDT concentrate in fat tissue and kill the adults of a type 1 species like the bald eagle, it hits them right at their most demographically vulnerable stage. It's devastating. If a disturbance destroys nesting habitats for K-selected seabirds, their entire reproductive output can be sliced in half in a single season. But conversely, if pollution adds a whole bunch of juvenile mortality to a type 3 fish population, it honestly might barely even register at the population level. Why? Because their strategy already accounts for massive juvenile losses anyway. Okay, quick checkpoint for you. Why is an increase in adult mortality so much more demographically damaging for a K-selected species than an R-selected one? Think back to our investor analogy. A K-selected species has poured practically all its energy into just a few offspring, banking on a long adult life to slowly replace itself. If you kill the adult, you wipe out a massive, irreplaceable investment of reproductive capital. An R-selected species, though? They can bounce back fairly easily as long as just a few lucky individuals are left to quickly pump out thousands of new offspring. Now try this textbook scenario on for size. Let's say a songbird population has 90% first-year mortality, but only 25% adult mortality. Which survivorship curve is this? Now, I know earlier we said many songbirds are type 2, the constant risk curve, but look closely at the data in this specific scenario. A massive, steep drop-off of 90% early on, followed by a leveling off to a stable 25% adult mortality. That steep initial drop followed by stability is the absolute classic signature of an early loss type 3 curve. It's a great reminder of why the actual data, and not just the broad species categories, is so critical to look at. Which leaves us with this final overarching thought. How must environmental policies adapt when managing a fast-breeding fish versus a slow-growing bird? We absolutely cannot use a one-size-fits-all approach to conservation. It's impossible. We have to look at the specific cards each species is holding and really understand the unique bets they've placed in the evolutionary casino. Because if we ignore their life history strategies, we seriously risk bankrupting the very ecosystems we're trying so hard to save. So, the next time you hear about a new conservation plan, ask yourself, are they protecting the day traders or the long-term investors? Thanks so much for joining me on this explainer. I really hope you walk away seeing the natural world just a little bit differently today.